in simple dynamo models. So just a quick overview of my talk. My main problem is, again, influenced by the solar dynamo and mean field dynamo theory I'm working on. So I'm just going to do a little background on those, but when I put my slides together yesterday, nothing much had been said about them, but there's actually been quite a lot said today, so I won't spend too long on that. And then I'm going to talk about the motivation for my work, which is looking at my fluctuating alpha effects and some previous work that's been done on that. And then I'm going to show you our 1D dynamo wave model, which is our, it's a 1D dynamo wave model. I'm going to explain that to you, and then I'm going to show you some of my numerical results that I've got from my models. So, the solar dynamo, despite the sun being a pretty chaotic object, it's got this very periodic structure in the magnetic field, which we see through the sunspot cycle shown at the top of the butterfly diagram. So it's interesting to know what's generating these magnetic fields. Obviously, it's the solar dynamo. This is believed to be occurring in the convection zone in the sun, where the flows there are quite highly turbulent and chaotic. Another interesting part of the sun is the fact that there's differential rotation plotted here. So the differential rotation extends throughout the convection zone, but then within the radiation zone there's uniform body rotation, so you get this thin layer of strong shear known as the tachycline at the base of the convection zone, and that shear and also the highly turbulent flows in the convection zone are quite important ingredients for the solar dynamo. So those both appear in the model that I'm using, which is the alpha omega dynamo model. This is where we split the magnetic field into its colloidal and toroidal parts, so it's an axisymmetric field. This is just a schematic of how this process works, which is quite a nice way to think about it. There's just a colloidal field starting on the left here, and this is twisted up using the large-scale shear or differential rotation that I showed on the previous slide, and twisted into a toroidal field. This is known as the the omega effect, and that's quite a well-understood effect. But then the difficulty is then closing the dynamo loop to get back to a colloidal field again. In this model, we use the alpha effect mechanism, which is where you use the small-scale turbulent motions within the convection zone to then twist the field up into a colloidal field again. The alpha effect is quite poorly understood, so that's why the work's been done on it. That's why I'm working on it. So just a quick derivation of how I get to the alpha effect using mean field dynamo theory. Starting with the induction equation at the top here, then we split our magnetic and velocity fields into their mean and fluctuating parts. Here I've used an overbar for our mean and the prime as the fluctuating part. And then the average is defined so that the average of the small scales over here is 0. So putting this into our induction equation, we can then write an equation for the evolution of the mean fields. And this looks pretty similar to the original induction equation, despite this new term, which is the EMF, which is a product of the fluctuations. And then to be able to solve this equation, we want to really write the EMF in terms of the mean magnetic field. So we use this expansion here, which has been described earlier today, so we'll look into that. The alpha term here is a pseudo-tensor, so it lacks reflectional symmetry, so that's quite useful in our helical flows. The beta tensor is a true tensor. In the simplest case, we assume isotropy and can write our EMF in this form here, where this alpha is the alpha effect I was explaining on the previous slide, which twists up toroidal field back into colloidal field. When this is used in most problems, alpha effect is usually assumed to be a constant, which is true, but it tends to fluctuate around this constant slightly, but that's fine considering the fluctuations aren't too large compared to the mean value of alpha. So on the left here, I've just drawn what we assume the ideal alpha to be, so it just tends to some non-zero constant, but it does kind of wiggle around it a bit. Excuse me. Now, there are cases where the alpha effect doesn't work as theory predicts it to. And one case is the Catanion-Hughes paper in 2006. Now, they studied a rotating layer of Boussinesq convection, and they had a helical flow, so therefore they should have an alpha effect, and this should then enhance the dynamo mechanism, and they should see a large-scale dynamo. But that didn't happen. They didn't see this large-scale dynamo. And so they calculated the alpha effect and plotted it against time to see what was going on, and this is what they got up here, which obviously doesn't look anything like what we expect alpha to look like. So it's wildly fluctuating, and if anything, it's tending to zero. It doesn't even have a sensible value. The plot below that is a cumulative average of the above plot, and even after long times, it's still really not tending to anything sensible. This example is an example of when your alpha effect is fluctuating, but you still don't get your large-scale dynamo. But there has been some previous work where they start with a fluctuating alpha effect and do see a large-scale dynamo, and they see this when you get your large-scale dynamo even when the mean alpha is zero, so purely due to the fluctuations of alpha. And the difference between this work is the fact that there's large-scale shear involved. So all of these papers here include they look at alpha in the dynamo model instead of the Catanion-Hughes calculation, which started from an alpha squared model, but there's no shear involved. So the first person to do this was Slatiev in 2000. He did quite a lengthy calculation, but only considered spatial dependence of the fluctuations of alpha. And then a simpler approach was taken by Proctor in 2007, but he only looked at temporal dependence of the fluctuations. So what I've been doing is taking the same calculation and adding in spatial dependence and to see whether we can still get this large-scale dynamo and to see whether it still occurs when the mean alpha is zero. And some preliminary results can be seen in this paper at the bottom. So I'll just explain my model to you. It's a 1D dynamo wave model, so it's just a simple model like a Parker model. A is a colloidal field and B is the toroidal field here. This term here is the alpha effect term, and then the omega prime there is our large-scale shear or differential rotation. Et is the magnetic diffusivity, and L is an inverse length scale. So to introduce large fluctuations in our alpha effect in this model, we split alpha into its mean and fluctuating parts in a similar way to the derivation of the mean field theory. Here I use a subscript 0 to denote the mean part and the subscript 1 to denote the fluctuating part. And our fluctuations are on time and space scales tau and xi. We also introduce this small parameter epsilon, and then we make this 1 over epsilon to make sure these fluctuations are large. Now that we have two space scales and time scales, we need to introduce a method of multiple scales. So our time derivative now becomes this, and our space derivative now becomes this. The reason we have a -half here is because of the double derivative, double spatial derivative in the equations, so that cancels things out. And by applying these, we induce these corrections to A and B, where these are again split into the mean and fluctuating parts. We define an average, denoted by these angle brackets, in a similar way to the derivation of the mean field theory, such that the average over the small scales is 0. And by applying all of this to our model, we can write a set of our equations for the evolution of the mean fields. And again, in a similar way, they look exactly the same as the original model, except this new term, which is a product of the fluctuations. So this is our new term that comes from our fluctuating alpha effect. We want to calculate this, and we can do that in Fourier space, which we see it's actually proportional to the gradient of B as opposed to being proportional to B, so it's definitely not a contribution to the alpha effect, it's something different. G here is just expanded on the right over here, it's quite complicated. It's associated with the square of the fluctuating alpha effect. And a similar corresponding term was found in the Proctor 2007 paper. However, that term was a positive definite term, whereas this term can now be positive or negative, which is quite important now. And it's very similar to the shear current effect, which was mentioned earlier. So it can be generated in that way as well, which Krior and Rogochevsky have hinted quite a lot. So now we've calculated what our new term is, we want to substitute it into this equation up here, and we want to solve our model to understand what's going on. And to do that, we seek solutions of this form at the top here. and we could get to a non-dimensional dispersion relation, which is shown here. Here we've scaled K with L and M as a constant. D is our dynamo number, which is related to the mean alpha. And Q is the dimensionless version of G that was on the previous slide. And that's associated with fluctuating alpha. So you can kind of see D is the mean alpha and Q is the fluctuating alpha on this slide. This graph here is showing where we plot Q against D squared, and then we plot lines of constant M all according to this dispersion relation. We see, because the G term from the previous slide I mentioned that it was a positive definite and we can now make it negative. That means Q can now be negative too. So just the region below this red line here is just showing the extra region of dynamo action we get from adding spatial dependence to the previous calculation. So there is more scope for dynamo action, but it's much harder to excite at higher critical values of the dynamo number. Another important part of this graph, we see that at this point here is where our dynamo number is 0, and that relates to our mean alpha being 0. So we do see dynamo action when the mean alpha is 0, which is what we were trying to clarify with the previous work. If you analyse what the dynamo number tells us, if we set that to 0, we should see steady solutions in that region too. So to understand whether we do or not, we need to solve the model numerically and see whether we get some steady solutions. So this set of equations here is just the analytic model from the previous slides, and I've just substituted it in the equation, the form for the average of alpha 1, B 1. So that's our new term there. So this is our mean alpha, and this is our fluctuating alpha term. And then to adapt this into a very simple model of the solar cycle, we just set our omega prime, so our shear, our magnetic diffusivity, and our inverse length scale to be 1, just for simplicity. And we set our mean alpha effect to be sinusoidal, so that it simulates antisymmetric waves about the equator. And we make it negative, so that these waves travel towards the equator. And then just a change of notation here, so our mean alpha is now becoming the letter D, and our fluctuating alpha now becomes R. So this is the model that we're trying to solve. I perform a linear stability analysis on this model in this case, and plot some stability boundaries in D and R space with the critical values of D and R for growing solutions. So they're shown on this slide. This is for varying values of L, increasing through the graphs this way. I've split the system into dipole and quadrupole systems. So the dipole is represented by the solid line, quadrupole by the dashed line. We can calculate the value of R when D is 0 using this formula on the right over here. And in these two kind of lines that you can see here, they're according to the first and second modes of stability. So the first one that goes up and then down here is the is n equals 1 in this formulation, and the one that comes from the top is n equals 2, and it's quite important to see that they actually meet at a certain point, which is a codimension 2 point, where you get a double zero eigenvalue, and then they continue down together. So at this double zero eigenvalue, eigenvalues to the left of this point, sometimes it's not quite left in this bit here, but eigenvalues to the left of this point are real, and eigenvalues to the right are complex, so we should expect to see some steady solutions on the left of that codimension 2 point, which again reinforces the fact that we expected to see steady solutions in the analytic model, and we should see oscillating solutions over here. And yeah, so the other thing that as L increases, according to this formula, R tends to a value of 4, and you can see as L increases through these diagrams, it tends to a value of 4, and both of the dipole and quadrupole branches merge together. So, to see whether we see our steady or oscillating solutions and understand what's going on there, we need to solve it in a nonlinear regime. Because it's nonlinear, I now need to add saturation, so I've just put in 1 over 1 plus b squared for each of the alpha terms. So again, D is the mean alpha and R is the fluctuating alpha. This is an ad hoc saturation. It's not exactly right, but then none of them are exactly right. But we are investigating different ways of putting saturation in, and it doesn't seem to change too much. And then we solve these equations in a box of size 0 to L, where 0 represents the North Pole and L represents the South Pole. So L/2 is the equator. So this sinusoidal part here, we see sinusoidal waves antisymmetric about the equator, which is what we wanted. And we make A and B vanish at 0 and L. And then we set this off with initial conditions of dipole parity, where A is even, B is odd, because that's the current parity in the sun. And so here's some of the results from that model. All of my nonlinear results are for a value of L equals 10. And here we also fix the value of D and increase the value of R. These plots along the top are space-time plots of the toroidal field, so kind of similar to butterfly diagrams. And you can see as you move along to the right here and increase the value of R, the period of the oscillations increases. And for a sufficiently large R, we do see steady solutions, which is interesting because for a normal alpha omega model, you don't see steady solutions as normally oscillating solutions. This is reinforced down the bottom here by the fact that we plotted our Fourier transform of the magnetic energy against the period, so we get a peak, and this moves along the axis at the bottom. So the effect of this R term is that it increases the cycle period. So this was for a fixed value of D. I can also vary that value of D. On the left here, I've got 3 different values of D for 5, 10 and 15, and I've plotted the period of oscillations against the value of R. And you can see that for each value of D, the critical value to see steady solutions for each value of D increases also with increasing values of R. So we can then plot the onset of steady solutions, which is done over in this graph here. So again, it's R against D phase space. These lines going up here are the onset of steady solutions for the dipole, which is the solid line, and the quadrupole for the dashed line systems. The bit down the bottom here is the stability boundary that I calculated in my linear model. And this little box down here is just a blown up version of what's going on in the middle there. And you can just see that that's the codimension 2 point for each of the systems, and the onset of steady solutions also meets at that codimension 2 point. So from the linear solution, both the linear code and the non-linear code, we've reinforced the fact that we see steady solutions over in the side of phase space. Another important part of this model is that as we were plotting this graph, we noticed that the simulations weren't sitting in the parity that we set them off with. So we set them off with dipole parity, and they'd occasionally flip into quadrupole or do something a bit strange. So we set them going with mixed initial conditions and let them run for a very long time and then see which parity they settle into. And this is just a preliminary graph. It's actually a bit more complicated than this, but of the stable parity throughout phase space. These 2 boxes are just blown up on the right here, just to show you that it's a bit more complicated than you can see in this diagram. And it's just interesting that for such a simple model, there's still quite a lot of crazy stuff going on. Yeah, that's all I really wanted to say. So just to summarise what I've been talking about, I've been looking at fluctuating alpha effect that has a spatial and temporal variation. And that we can, as the previous work suggests, see a large-scale dynamo that works even when the mean alpha is 0, so which is purely due to the fluctuations. By adding in the spatial dependence to the Proctor calculation, we get a larger region of possible dynamo action. And that this new term that arises from the fluctuations means that we can increase the cycle period. We see steady solutions at a particular value of R, and there are points where there are no oscillations, so that's quite an interesting point. And there's complex parity structure throughout the model. And then the next thing I'm just trying to do is to take my original 1D dynamo wave model and to actually put in a random function for my alpha effect, and to see if it shows the same thing, so to see if my cycle period does increase, to kind of back up this whole mechanism. That's it. Thank you.
Thank you. definition of R, can you remind me again? What was R? It was related to Q, right? Or
yeah, it's a bit confusing, the notation. R is basically the... Oh, sorry.
Yeah, there was.
R is basically this. And then, so Q is the non-dimensional version.
G,
so G here. Yeah.
R is G, you say?
Yeah.
Yeah, okay. Yeah, exactly. So when do you find this to be zero? I mean, do you can you give any conditions when it becomes zero? Because that's a new feature which you get with the spatial fluctuations, of course.
Yeah, well, when I set R or G, whichever, to be zero, then I've just got the normal model with just the alpha effect. That's zero. Then there's no extra term, so it's not.
Yeah, but I mean, from the terminals, what is the property? I mean, what enters is the microscopic diffusivity.
Mm-hmm.
So you might expect that if you change the Reynolds number, or perhaps the Strohal number, or something like this.
Yeah, I'm not sure. I haven't done that, but I mean, everything's scaled to 1 in my simulation, so it's not trying to be anything.
So for you, it's more like a free parameter at this point.
Yeah, yeah. It's just like both my mean and fluctuating alpha are just parameters that I vary. That's why I'm trying to back it up with actually putting a fluctuating, like a random function in. But they are just numbers that I put in at the moment. So.
Any other questions? Please, yeah.
What is R?
Sorry, say that again.
What is term R?
That's this term here.
Maybe show again the previous. You had another. Where you actually had the definition.
Can you show next slide?
Yeah, sure. Next one.
Oh, think.
Yeah, RSG, I see.
Yeah. It's literally just notation change. Like, can't change one without the other.
Yes.
Sorry to be confusing. Okay.
Okay. Yes, Matthias?
The new contribution due to the fluctuations is vanishing if the differential rotation is vanishing, right?
It's...
As I learned from your formula. And that's a bit surprising for me because an old derivation by Motter showed that fluctuating alpha creates more or less something the same like a negative diffusivity. And is not necessarily connected with differential rotation. So why is this negative diffusivity effect not visible here?
No. I'll have to think about that.
I understood correctly that the new contribution would disappear if the differential rotation is zero. Because it's proportional to omega.
Yeah, so it's got an omega in.
That's
Yeah,
right.
yeah. That's how I'd see it, but I didn't know that. But I'll look at this.
I think that's probably a consequence of the approximation. You made it something like an upper omega approximation.
Yeah.
Assume strong shear.
Yeah.
Yeah. I mean, what Matthias is referring to is the... I mean, there's an earlier result by Craignan, which showed that in the absence of shear, you can get a dynamo action from a fluctuating alpha.
Yeah.
But then you can't get large-scale magnetic fields. For that, you do need shear.
Yeah.
But I think nevertheless, formally, your new additional term here is acting like a negative diffusivity.
Yeah, well, there's been stuff, I mean, it's thought to be part of the like off-diagonal components of the beta tensor anyway. Still trying to work out exactly what term it is. But it's definitely not an alpha effect term, it's something different, but I'm not entirely sure.
But you rather think it's perhaps a shear current effect, yeah?
Yeah, yes. I mean, the shear current effect arrives that it's the same sort of term, but a different formulation in the first place.
Okay. All right. So, and thanks. And now we have the next talk by, if I were able to pronounce your name correctly, Najdina, or how do you pronounce your name?
Just Nadia.
Huh?
Just Nadia.
Nadia. Yes, that's easy. So Nadia is presenting a talk about sunspot fluctuation, sunspot statistics from and the north-south asymmetry in sunspot records. So they come closer to the solar dynamo again, or the stay with the solar dynamo, I should rather say, and stay with the fluctuations.